Hello everyone, my name is Pedram and I'm a professor in data analytics. Welcome to another episode of Deep Learning. Alright, this is the Python part for our module number 5, Deep Computer Vision. As I said it earlier, this is a long module and I'm going to do it in 4 theory parts and 3 Python lectures. So this is the first lecture from the Python series for computer vision. Okay. So you should navigate to my GitHub account and then there go to the Deep Learning USU folder, go to Lectures and Code, and then go to Deep Computer Vision, then to Python. So there are 3 files here and I'm gonna record the video for each of these files. In the first one, we'll start with the very basic neural networks, no CNN, using MNIST data. For the second one, we are going to use data augmentation and apply that data augmentation as a regularization to the fashion MNIST dataset. And then finally, we are going to talk about the concepts of transfer learning, and we will be using real images for transfer learning. So we are going to use a dataset from Kaggle competition and apply transfer learning to that dataset. Okay, so without further ado, let's start with the very basic CNN using the MNIST dataset. Let's go ahead and click on it, and you should be able to open it in a Google Colab by clicking on this link. And I'm gonna go ahead, make sure that the runtime is GPU. So this is a free version of Google Colab. You should see something like this. I'm gonna go ahead and connect. And I want to make sure that all the outputs are clear, so we're going to generate the outputs together and make necessary changes if required. Okay, so let me go ahead and minimize this bar, and yeah, we are connected. Let's go ahead and do this. So again, Deep Computer Vision, CNN, we're going to start with the very basic data set. Okay. So if you want to run things in Google Colab, let's go ahead and continue. If you want to run it in your local computer, hopefully you have GPU. Otherwise, because from this lecture we are doing image processing, computer vision, you absolutely need to have access to GPU. Otherwise, the training part of the model is going to take so long on your CPU. Okay, so let's quickly check the version of the Tensorflow. So as of February 2023, this is 2.11, and I'm going to go ahead and import a bunch of packages for data manipulation and visualization: pandas, numpy, matplotlib, and later on I'm going to import Seaborn. Okay, so let's look into the dataset. As I said, the dataset is called MNIST. So this is a very famous dataset for image classification. Basically, here's a sample of the data set, right? Basically, these are handwritten digits, and our goal and objective is to make sure that the model is able to figure out what are these numbers. So some of them are easy, some of them are more difficult, but the idea is that using CNN, we should be able to get a very good accuracy in the test set, and this is exactly what we're going to do. Okay, so this data set is a very classical one, and it obtains 60,000 training images and 10,000 test images, and the size of the image is 28 by 28 by 1. So it means that it's a grayscale image and it only have 1 channel. Okay, so let's go ahead and import that. So a good thing about this dataset is that it's already built in the keras library. So we can go ahead and say from tensorflow.keras.dataset, let's go ahead and import MNIST and then load the data. Okay. So the way that the data is loaded is we have a tuple of input and output. You can go ahead and call it anything, but I like to call it X train, Y train, an X test, Y test, in the same way that we did for our machine learning problems. But for computer vision, people may call it, for example, image train and image test, and then label train, label test, something like that. But I think we can keep things simple and just call it X and Y. Okay, so one thing that I want you to become very familiar is the shape of input and output, because especially in computer vision, when you're dealing with images and sometimes real world images, it is really important to get a good understanding of the size of the input, size of the images, right? Because later on you need to pass it to different architectures and you need to know how to play around with changing the shape of the inputs and different layers, right? So let's go ahead and see what is the shape of the X train. So the shape is 60,000 by 28 by 28. So right away, I know that if I want to pass it to a CNN convolutional layer, I have to add the channel shape as well. So I have to reshape this one to a 60,000 by 28 by 28 by 1, right? So this is right away, this is one change that we need to make. Okay, so the shape of the test set, again, 10,000, 28, 28. We can, for example, look at the first observation in the train set. And as you can see, this is what computers see, right? So we talked about it in the lecture in the, where is it? In the lecture for the basics, that we were talking about what computers actually see. So this is what computers see. It's a matrix, right? So this is what the computer see for image number 1 in the train set, right? We can visualize it. We can, from matplotlib, we can use this function to image show, im show, and then we say, okay, let's go ahead and show the first image from the train set. I'm going to change the mapping, color mapping to gray to make sure that this is a gray picture. Originally it is saved as a gray picture, but if I remove this one, it's going to use the default coloring mapping, and the default one is something like this. So don't get confused. This is not a colorful image. So this is just a CMap that is used by default. So that's why I went ahead and changed the CMap to just make sure that these are black and white images. Okay, so this is our first observation in the train set. It's number 5. Okay, so if you look at the label better be 5, right? So let's go ahead and run this. There you go. So the label for the first observation is 5, second one is 0, and etc. You can go ahead and look at the second one as well. So it should be 0. So this is our 0, and etc. Okay, now let's go ahead and construct our very first convolutional neural networks. So we're going to import from TensorFlow, import TF. Well, import TensorFlow as TF, and from TensorFlow we are going to import Keras, and from Keras we're going to import some layers. So we have done this before previously, and again, as I said, the shapes are important things. So I'm going to go ahead and reshape XTrain to a tensor of 60,000 by 28 by 28 by 1, because this, if I want to pass this to a CNN, the TensorFlow model is looking for an input shape like this. Okay, so that's why we're going to go ahead and reshape it. One other thing that we usually do is just scaling the features, right? It's scaling the inputs. We know that each pixel is a number between 0 and 255. We're going to scale everything to be between 0 and 1. So this is going to help us when it comes to calculating the gradients or feed forward, backward propagation, and things like that. And it's going to speed up the process. Okay, so let's go ahead and do that. We're going to do the same thing for both the train set and test set. Okay. We don't need to make any changes to the labels because labels are just pretty fine. There are tensors, and it goes from, let's say, again, with the size of for train is 60,000, for test is 10,000. All right, so now we can look at the shape of the train set again. Now it is 60,000 by 28 by 28 by 1. The same story for X test, 10,000 by 28 by 28 by 1. Okay, now the input is ready. Let's go ahead and construct our neural networks, the CNN, and then let's see how it performs. Okay, so I'm gonna go ahead and basically build my first neural network using a function. The reason we talked about it in the previous Python videos, the reason that you do it this way is that because each single time that you run the model.fit, it's gonna go ahead and update the weights on top of the previous trained model. So if you want to avoid that, if you want to make sure that every single time that you call the model fit, it's fitting on the new weights, so initial weights, and then the update from there, you have to make it as a function, and every single time you're going to call that function again, reset the weights to initial values, and then do the training. So we do it because you want to play around with different architecture in the model, sometimes with different for example, number of epochs we use, different callbacks, and for example, different regularization, right? All right, so let's see what is inside this one. We are gonna start from an input layer. So from keras.input, remember the shape is the most important thing that you should be aware. So the shape is this is a shape of one instance in the train set, right? It's one picture, one image, 28 by 28 by 1. I go ahead and give this input layer a name. The name is basically input layer. Then on top of this one, I'm gonna build some other layers. So let's start with a very simple convolutional layer on top of the input. So this convolutional layer has a filter of size 32, and we're gonna use 32 filters. The size of the filter is 3 by 3, so we're gonna use a kernel size of 3. The stride is 1 by 1, so by default stride is 1. So if you don't specify it, it's automatically is 1. Again, padding by default is valid. So valid simply means no padding. Basically use the valid pixels in the real image instead of assigning zeros to the borders, right? And activation function is relu, and let's call this layer our convolutional layer number 1. So this layer is built on top of the input layer. So remember, we have talked about all these things in the previous videos, that this is a functional API that we prefer to use for this course. We're not going to work with a sequential kind of API, or neither that one nor the subclassing API. So something in between. You know, this is very practical when it comes to handling almost any kind of problems in practice. Okay. Then on top of that convolutional layer, we're doing a max pooling of size 2, and we can call this one our pooling number 1. Then again, we're going to do another convolution max pooling, another convolution, and then finally we're going to flatten. As you can see, when we go deeper down in the network, we're going to use more filters, simply because the dimension of the feature map is going to be smaller. We have the luxury, we can afford adding more filters down as we go deeper in the network. Okay, then finally we're going to flatten this thing. I can call it flattening layer, and then we can use a dense layer after flattening. That dense can have 64 units or 128 or whatever. You can try different numbers and see which one performs better. I'm going to apply a relu activation function to that dense layer, and then that's it. Finally, we're going to have an output layer. So the output layer is a dense one with 10 units, because we have 10 digits from 0 to 9. Basically, this is multi-class classification with the activation function softmax. And I'm going to call this output layer. And finally, we are ready to just put this together. So this is our model, and this function is going to output this model, right? And the model is keras.model. We're building the model here. We are literally building the model by running this line. So we say inputs are the inputs here, and outputs are the one that we just created, and then we can call it my first CNN model. Then finally, we're going to put the model compile inside this function. And for compile, we're going to use RMS prop optimizer. You can go ahead and try Atom. But for some simple data set like MNIST, honestly, both of them, any kind of optimizer should do the job. And our loss function is a sparse categorical cross entropy, because remember, this is a multi-class classification, but the output is 0, 1, 2, up to 9. They're kind of ordered, right? So means that, for example, number 2 and 3 are close to each other. So for that reason, because the multi-class classification, the output is integer in this case, we can go ahead and use sparse categorical cross entropy. If it was multi-class classification with different, I don't know, objects like, is it a cat or dog or another animal, you know, let's say 4 class classification between different animals, we could have used categorical cross entropy with the difference that we had to make sure that our target variable was 1-hot encoded. Okay, so here we didn't need to 1-hot encode our target variable, because we are using a different loss function. We're using a sparse categorical cross entropy. And again, you can go ahead and give it a try. You can change your target variable. You can 1-hot encode that one, And then if you want hot encode your target variable, you can go ahead and just use categorical cross entropy. You don't need to use sparse categorical cross entropy. All right, and for the metrics, let's go ahead and use accuracy. Now this is, the model is this, let's go ahead and define this function, call it CNN builder. Now I'm going to construct a model. So when I say model is equal to CNN builder, so then I can look at the summary. This is what we have inside this model, right? So now this is a summary of your first CNN model with basically the three convolutional layers, two max pooling layers, and one flattening layer and a dense layer, and finally an output layer. So this is the output shape at each layer, right? So at the very first layer, so this is our input layer. This is, remember, 28 by 28 by 1. This none basically means that the number of instances, right? It can be anything. So here for train set, we have 60,000. I can pass anything to this model, right? I can pass the test set, so this none is going to become 10,000. I can pass a single incident, so this none can be 1, right? So of course the input layer, there's no parameter. Then the next layer, we go from 28 by 28 by 1 to 26 by 26 by 32. So where are these numbers coming from? So if you have remembered from the lecture notes, we talked about the details on a couple of slides. So here we said that how we can calculate these things. So make sure that you watch the theory lecture before you watch this one, or if you're curious how these numbers are calculated, right? So we said that there's a formula that tells you what is the size of the, let's say, output layer compared to the size of the input layer, and the padding, and this was the filter size, stride, and +1. So we can go ahead and quickly do some of these calculations, right? So for example, where is this 26 is coming from? 26 is 28, no padding here, so +0, minus f, which is the number of the filter size, right? Which was, our filter size was 3. So 28 minus 3 divided by 1, which is a stride. So it's 25 plus 1, which is 26. So this is where the 26 is coming from, right? You can and then we're doing a max pooling. So this 26 is almost halved. So we get 13. Then we have 32. This is the number of filters in the convolutional layer. So here we have 64 number of filters in the convolutional layer number 2, and then 128 number of filters in the convolutional layer number 3, right? So then we're going to flatten things. So it means that if you do 3 by 3 by 128, you should get 1152, because we're simply flattening the last convolutional layer. And let's look at how we can calculate some of these parameters. So for example, where is this 320 coming from? So this 320, remember, this is a grayscale image, so it means that it has only one channel. So this means that if the filter size is a 3 by 3, so let me actually try to find something here, maybe quickly review that one. We can do, let's say this is a 3 by 3, right? So we have a 3 by 3 filter, so it means that we have 9 parameters here. And because there's only one channel, we need to multiply it by 1. And then how many of these filters we want to apply? So it's, again, one channel, multiply 3 by 3, multiply 32 filters in the first layer, first convolutional layer, plus 32 terms for as a bias term that we're adding it. So if you do the math, you are going to get your 320, right? So how about this one? Again, you have to see what was the size of the channel or filter in the previous level. So it was 32, okay? So 32 multiply a 3 by 3, this is the size of the filter, multiply how many filters we're using in this layer, 64, plus 64 numbers for the bias terms, right? Okay, and you can go ahead and try to figure out what is this one and this one, and then finally we are looking at what are the parameters in the dense layer, right? So again, just make sure you can follow these numbers. And finally, this is the flattening part, now 3 by 3 by 128. And then finally, this has been flattened. We are gonna do something like this. So we have, well, actually I added this dense layer as well. So let me go ahead and show you how to calculate that dense layer, the parameters too. Okay, so actually this belongs to the previous version, so we have to do it again. So this is a flattening layer, and then now we have literally 11 to 52. We have to multiply that one by 64 because this is the next dense layer, and then add 64 bias terms, right? So let's do that. 1152 multiply 64 plus 64. So we are gonna get 73,792. So this is how this number is calculated. And finally, the last output layer, this is easy to calculate, right? So in the previous layer, we have 64. So it means that we need to multiply this 64 by 10 nodes in the output layer. So we get 640, and we need to add the 10 bias terms, so which is 650. Okay, so hopefully you can calculate these numbers if you wish, if you're curious how to do the math, right? We're going to add up all these numbers. So this is the total number of parameters that we have in the model. So during the training process, these parameters are going to be updated to minimize the loss function, right? Okay, using backpropagation. Okay. So, and again, here, just for your reference, the formula that we use to calculate the output shape at each layer, right? So for example, for the first one, we got number 26. Okay. All right. Now let's go ahead and fit this model. So I'm going to go ahead and create a callback, basically a model checkpoint, simply because we want to make sure that we see the performance of the model in our best epoch, right? So let's see, I'm going to go ahead and say from TensorFlow callbacks import model checkpoint. Let's go ahead and create that checkpoint. So this is going to be, I'm going to call it first CNN, and it really doesn't matter if you save it as Keras or H5, because this is a super simple basic model. We're not going to make any customization, so I can go ahead with H5 because it's simpler. It's just one file and it's lighter. Okay, and we're going to say save best only yes, and we will be monitoring validation loss, right? So let's go ahead and run this. And now this is the training part, okay? So I'm going to go ahead and click on this. This might take some time. I'm going to pause the video and show you when it's done, okay? So we're going to run things for 10 epochs. The batch size is 64. Our callback is just model checkpoint. Make sure that this callback is a list, because that's what TensorFlow is expecting for the callback. And we're training the model using train set, and the validation set is basically our test observations. Okay, so then obviously if you know where's this number 938 is coming from, if you multiply this by the batch size, you get that training size. Okay, and you're repeating this 10 times, so this is not that long, so we are halfway through. And as you can see, this is a loss and accuracy in the train set. This is a loss and accuracy in the validation set, right? So right from the beginning, the model is doing a very decent job, and it started increasing to 99% accuracy in the second epoch, right? And then it seems that right off the batch, the model is able to do a pretty good job in the validation set, okay? So this is the last epoch. Let's let it finalize the model. And then we are going to go ahead and actually let me show you this folder. If I go ahead and refresh it, it's already there, right? So this is our H5, the saved model, the best version of the model which is saved using model checkpoint, right? So the first best is saved, right? We can go ahead and change, for example, change it to false or something like that, right? We want to save the best only here. Okay. So now I want to see how this model performs in a test set. I'm going to say that, okay, let's go ahead and create a model, test, we can call it test underscore model. This is, we're loading this first CNN that we created, right? And remember, whatever is inside this one is the best model, okay? Then we're going to evaluate that model based on some new observations. So basically here's the test set. So if I go ahead and run this, that will be the 99+%, right? So again, right, using a very simple CNN, the model is able to predict the handwritten digits with plus 99% accuracy in the test set. Another way to do that, you can go ahead and, for example, from the train set, create a validation set with 10,000 or 15,000 observations. Because this data set is relatively large enough, we can do that. We could have done that, right? We could say that out of that 60,000 train set, let's use 40,000 of it, or 45,000 of it, or 50,000 of it as the train set, and the rest as a validation set, and do not touch this one, and use this one at the very last, that we want to see the real performance of the model in some data that the model has never seen, right? So here we are cheating a little bit, but again, this is just a simple example. In more real world examples, images, I'm gonna do train, validation, and test set. Okay, all right, so that's it. Now let's go ahead and do some of the plots, right? So let's look at the epoch versus performance metric. I'm going to go ahead and look at what are the available metrics inside this model. So right now we have loss and accuracy, and we're going to go ahead, let me actually minimize this again. We're going to go ahead and create our data frame, right? So this is the way that I prefer to do it. You can do it anyways. Usually because this data frame is not that large, that's the length of it is the same as the length of epochs. So it's not going to slow down anything here. We're going to use pandas. And history, remember, everything is going to be as a dictionary in the history when the model has been trained. And let's see what is inside that metric, right? We can look at the head of that data frame. So again, depending on how many the epochs you have here, we had 10 epochs, so I can go ahead and remove this head. So there's going to be 10 observations, right? So this is 0 to 9, 10 observations for 10 epochs. Loss and accuracy in the train set, loss and accuracy in the validation set, right? And now that I have it in a nice data frame, I can do visualizations a lot easier. So for example, I can say from this metrics, just pick up the validation loss and validation accuracy. Accuracy. We can do both loss and accuracy and validation accuracy in one graph. This is what we see, and loss and validation loss in another graph. Okay, so again, it seems that right from the beginning, model is doing a decent job, right? And maybe at the fourth epoch, we get to the minimum loss, which is corresponding to maximum accuracy in the test set, right? So usually we want to see something like it start decreasing and then goes along this. But again, right off the bat, the model is performing awesome, right? So it's 99%. There's not much room for improvement. Okay, so now we want to see what are the predictions, right? So if I go ahead and run model.predict, and of course we want to make prediction in the test set, this is going to give me some predictions probabilities. So let me tell you what I mean by that. So inside this prediction probabilities, remember we had, for example, 10,000 observations for the test set. There's going to be 10,000 records like this. I'm showing you the first one. So this is it. Again, the output is this. Let me actually show you the dimension. So if I go ahead and say predictions, probabilities, if I type it, it's faster. The prediction prob dot shape, it is going to be 10,000 by 10, right? And so it means that 10,000 test observations, and for each one we have 10 numbers. So these are probability assigned to each class, right? To each digit in this case, right? From 0 to 9, because we used simply the softmax. And for the first one, if you look at that, where is this probability max, right? You can use NumPy argmax, or you can visually see that. Right, so this is to the power of minus 13. So these are very small numbers. And then this is our largest one, right? So if you count it, so it's 0, 1, 2, 3, 4, 5, 6, 7. Number 7 is what the network is going to output. Let's look at that. Okay, 7, yeah. So this is what the model predicts for the first hand digit, which was, let's say, number 7. And in the test set, the label was actually number 7. So of course, the model is doing a great job here. All right, now, if we want to visualize things, we may not want to work with this prediction probabilities. We want to see what are the classes, right? So we want to see, for example, for the first observation, I want to see number 7. So how do we do that? So in general, for binary class classification, we can simply use numpy where. If the predictions are greater than 50%, call it 1, otherwise 0, right? For multi-class classification, we can look at numpy argmax, right? So for example, if I look at the argmax of these numbers, the output is going to be 7, right? So now let's do that, right? So I'm going to say these are the prediction classes. Prediction classes are equal to numpy argmax. I'm going to pass this prediction probabilities, and x is equal to 1, right? So let's look at the first 5 predictions. Again, the first one is 7, the second one is 2, 1, 0, 4. So these are the actual predicted classes, right? So instead of seeing a vector of size 10 different probabilities, I see one number. Now we have predictions, we have actuals, we can do classification reports, right? So from scikit-learn metrics, I'm gonna go ahead and import classification report and confusion matrix, right? So this is why I prefer to come up with, I don't know, a data frame like this and get access to the predictions and actual values like this, simply because I can leverage some functions from scikit-learn machine learning package and then to see things a lot easier, right? So let's go ahead and import those metrics. And I'm going to go ahead and look at the classification report. So this is a built-in classification report function in scikit-learn, right? So you need to pass the y-test, actuals versus predictions, and the ordering matters for some applications, right? So here, for some of the metrics, the ordering matter. So here, this is classification. And now, for example, in regression, we know that the ordering, if you're doing mean absolute percentage error or things like that, the ordering matters. If you go from actual to prediction compared to prediction to actual, right? But here it really doesn't matter that much. So this is the precision recall F1 score, basically the classification report for our 10 classes, numbers 0 to 9. And as you can see, the F1 score is perfect, right? So this is perfect, even in the test set. And when you look at the precision recall, the same story. The model is doing an excellent job. I can go ahead and look at the confusion matrix. Again, along this line, it seems that the model is doing a perfect job, right? There are some misclassifications here and there. So for example, we have six misclassification here, which is, well, actually, let me use Seaborn and do the heat map, and we can see things better there. So from Seaborn, I'm going to do a heat map for the confusion matrix, right? So now we can see where those misclassification is happening. So for example, here, it seems that the model is having hard time between classifying digit number 9 and number 4. So 9 and 4, so the model is having hard time classifying these things. And hard time is relative, right? The model is doing a 99% plus accuracy in the test set. But still, there's 1% that the model is not capturing, or less than 1%, which is among these numbers. And for example, between, what is this? We have 3 misclassified between 5 and 3. So 5 and 3 is another thing. We have 2 misclassification between 3 and 2. And yeah, let's look into some of these misclassified observations in a test set. So I'm going to run this line just to show you what is inside this. I'm going to say if the y-test is not equal to the predictions, right? So this is going to be a bunch of booleans, right? False and trues and false, right? False. So I'm going to go ahead and create a misclassification object. I use a list comprehension. I say that I for these I and x in enumerate of this. So basically I'm looping over 2 things because I'm doing enumerate. When I do enumerate, this thing is going to tell me that, first of all, what is the index number and what was the output. So this is the index number and the output, right? And I say if the output is equal to true. So this means that if the test set, if the y-test is not equal to prediction, basically if it is misclassified, go ahead and tell me what was the index. Okay, so now I can go ahead and show you the first 9 misclassified indices, right? So these are the indices. So observation number 18 from the test set, number 115 from the test set, number 740 from the test set, and etc. These are misclassified. Now that I have these indices, I can go ahead and plot them, right? So how do we do that? I'm gonna go ahead, actually, let me show you something. Let me show you the test set size. So for example, if I do X test, and the first observation in the test set, what is the size of that? It is something, well, I need to see what is the shape, right? So the shape is 28 by 28 by 1. If I go ahead and use the plt.imshow, image show function, if I simply pass this, it's going to complain. Let me show you the error message. Again, this is something that I told you that you should become familiar when you want to visualize things, when you want to play around with the input shape, output shape, and etc., especially in computer vision. So if I just run this line, it's going to complain because, well, it worked here. Well, here it didn't complain. Let me see. So it seems that I didn't need to reshape this one. Even if I do reshape, it's going to still work. Okay, so yeah, so we didn't need to reshape here, but for real image and for some applications, when we do plt.image show, it's going to complain about the shape, and we need to make sure that we have reshaped the image the way it is appropriate. Okay, so here it didn't complain, so I can go ahead and just simply remove this, right? So again, here basically we don't need this one, and I can say, okay, for I and number in this enumerate of misclassified images for the first 9 images, let's do something like this. I'm going to do subplot and then just visualize it in a 3x3 graph, right? So let me actually go ahead and run this, and I'll walk you through to the code. Okay, so what do we have? We have the index number and the actual number which was misclassified, right? So we want to see the actual number that was misclassified, so we don't care about this index. So I'm going to use this number. This index is also used just for, tell me that this is 3, 3, 1. So this is a 3x3 plot. The first one, when I is equal to 2, second one, third one, fourth one, and etc. And the actual number inside that is going to be plotted like this. Okay, so the first prediction, I don't know, it seems that it is 3. And by the way, we're going to save the actuals as well, because we're going to compare what was prediction and what was actual, right? So I'm going to use a simple append here. All right, so I don't know, maybe it seems that it is 3, this is 4. Let's look at the numbers before, let's look at the actual labels before making a guess, right? Okay, so these are the actuals, these are the predictions, okay? So it seems that, yeah, actuals, it was a 3. The model predicted as a 5. The second one, well, let me actually show you a list. We can compare them side by side. Okay, this is easier to match them, right? So I can say the actual for the second one is 4. The model predicted 9. Okay, then this is the actual was 3. The model predicted 2. This is maybe the difficult one. The actual was 5. The model predicted 3. This is the tricky one also. The actual was 3. The model predicted 5. As you can see, between 3 and 5, model is having a hard time, right? And this one, this is really, honestly, very weird, even for us, the humans, right? So what is this, right? So actual is 8, and the model predicted 2. And I don't blame the model for that, right? Because honestly, this is hard to, label it. This is also difficult. Remember, this was a model that performed 99+% accuracy in a test set. So these should be weird numbers, right? Weird observations in a test set. This, I don't know. In reality, it was 2. The model predicted 6. Again, I don't blame the model here. This in reality again was another 2. The model predicted 7, and last one in reality was a 4, and the model, I think, it has every right to predict to classify this one as number 9, right? Okay, so that was pretty much it. This is everything we needed to know for running our very first basic CNN. in Python using TensorFlow. Until the next one, take care.